It was a holy moment. The Andromeda Nebula overnight became the Andromeda Galaxy. For years, our understanding of the Andromeda Galaxy was limited to ground-based observations. However, with advancements in technology and the birth of the James Webb Space Telescope, our understanding has grown beyond measure. Now, things are about to change as the James Webb Space Telescope has detected alarming signals coming from the Andromeda Galaxy. These signals have sent shockwaves through the scientific community, leaving astronomers both inspired and curious. But what exactly do these signals mean? Most importantly, why are they causing such a stir among astronomers? Join us as just 2 minutes ago, the James Webb Telescope shut down after receiving alarming signals from the Andromeda Galaxy. Before we could see far beyond our eyes into the cosmos, astronomers believed the Milky Way to be the whole universe. This lack of insight was primarily due to limited technology for seeing various galaxies and individual stars. However, everything changed when we discovered the Andromeda Galaxy. It served as our first hint to knowing that the universe stretches far beyond the Milky Way. In human imagination, it all began in the 17th century when Galileo Galilei's pioneering work with telescopes revealed the Milky Way's true nature. He saw that the Milky Way had numerous stars, challenging the prevailing idea of its singular importance. Everything changed in the 1920s when Edwin Hubble discovered distant objects beyond the Milky Way using the Hooker telescope. Edwin noticed that these celestial objects moving through the cosmos were galaxies, different from the Milky Way. One of the galaxies was the Andromeda Galaxy, or M31. While this was the first time we were seeing the Andromeda Galaxy through a telescope, Persian astronomer Abd al-Rahman al-Sufi first noted it around the 10th century. Thanks to the technological advancements in the 20th century, astronomers could see and understand the true nature and essence of Andromeda. Andromeda is a nebulous cloud consisting of a vast galaxy of stars, similar to our Milky Way. Our cosmic neighbor is approximately 2.5 million light-years away from the Milky Way. Since its discovery, the way we study Andromeda has profoundly evolved. We have moved from ground-based observations through telescopes to space observatories like the Hubble and the James Webb Space Telescope. Each advancement in technology has taken us to new heights, helping us understand the secrets of the Andromeda Galaxy. We now have more information and insight into its composition and structure, making Andromeda a benchmark for studying the formation and growth of galaxies. This has shed more light on the broader working principles of the universe. Scientists believe that to have a better understanding of our universe and the Milky Way, we must study the relationship between Andromeda and the Milky Way, especially given that both galaxies are bound to collide in approximately 4 billion years. While studies and investigations have progressed, the James Webb Telescope recently received a concerning signal from Andromeda. This alarming signal baffles scientists worldwide, prompting questions about its exact origin and potential implications. The James Webb Telescope's advanced sensors have detected unusual activity right inside Andromeda's core. The signal sent back to scientists shows results that significantly differ from past observations, intriguing scientists worldwide. The signal indicates major processes going on within the galaxy, potentially linked to its supermassive black hole or previously undiscovered occurrences. Notably, one of the latest findings indicates that Andromeda's mass may be much bigger than that of the Milky Way, reshaping our understanding of both galaxies' sizes. The James Webb Telescope has also provided detailed images and spectra of Andromeda, unveiling the formation of new stars and their chemical compositions. This new data is important for understanding galactic evolution and potential conditions for life. Additionally, the data from the telescope suggests increased activity in Andromeda's active galactic nucleus, ultimately impacting its surrounding environment and shaping its future structure. Furthermore, by looking into the gravitational effects on stars within Andromeda, researchers gain insights into the distribution of mysterious dark matter throughout the galaxy, hopefully furthering our understanding of its influence on the dynamics at play in the cosmos. As things are, understanding dark matter and its impact on the universe is one of astronomy's greatest puzzles. Recent breakthroughs by the James Webb Telescope have motivated various studies worldwide as scientists look into the secrets of Andromeda. With more information coming to light, we now know more about the galaxy's past and future. So what have we learned about the Andromeda Galaxy through various studies? Andromeda has shown impressive characteristics that distinguish it from other galaxies spread across the universe. Its sheer size commands attention, with recent assessments suggesting a diameter spanning around 220,000 light-years. This figure makes it one of the largest galaxies in the local group, even bigger than the Milky Way. This vast scale contributes to its mass, consisting of an estimated trillion stars, surpassing our galaxy in stellar count. Researchers also find the G structure fascinating. Unlike a typical spiral galaxy, Andromeda has a bulging center and a dense nucleus enclosed within rings of dust and gas. This is undoubtedly a fertile ground for ongoing star formation, such features showing a dynamic galaxy created by continual processes shaping its evolution. Among its many features, one of particular interest is its nucleus, characterized by a double peak emission hinting at the presence of a supermassive black hole, similar to but different from the Milky Way's. This offers important insights into the nature and activities of these massive matter-eating holes. Andromeda is also encircled by a sphere of stellar debris consisting of stars, planetary and globular clusters, spanning hundreds of thousands of light-years in diameter. This cosmic covering tells a captivating, detailed story of the galaxy's unique origin and history. The 460 globular clusters found in Andromeda also offer insight into the formation of stars in the very early stage, providing a clear explanation of the formation of star clusters and the early development of the galaxy. In piecing together the mysteries of Andromeda, astronomers are one step closer to understanding the cosmic relevance of dark matter. However, one question lingers: how do they account for its mysterious nature and the role it plays in the dynamics of galaxies? Andromeda boasts another distinctive feature: its satellite galaxies. Its halo structure is made up of more than 20 smaller galaxies, and some of them are undergoing tidal stripping of their stars and gas. This process involves a larger galaxy pulling in and destroying neighboring small galaxies, displaying the active nature of cosmic evolution and portraying how galaxies grow and interact with each other over time. So what does the future hold for the Andromeda Galaxy? The shape and direction of its movement fascinate not only astronomers but also those seeking to understand the cosmos. The possibility of its transition from a spiral to a ring galaxy is centrally strategic in Andromeda's development. Evidence points to a process that could lead to other rare combinations, possibly from galactic collisions or close interactions with other galaxies. If Andromeda is indeed moving in this direction, it means that it has experienced many interactions with other galaxies since its birth. Ultimately, Andromeda's future depends on the imminent collision with the Milky Way. According to these models, the collision is estimated to occur roughly 4 billion years from now. The result of such a collision is the birth of a new galaxy from these two giant celestial entities. Though destructive, the collision is a natural part of galactic development. However, due to the vast distances between the galaxies, this galactic collision isn't a direct impact. After the collision, both galaxies would be radically restructured, forming new shapes and compositions. The interaction of their gases and dust will stir up new rounds of star creation, leading to a large spectacle in the sky as the merging objects twinkle brightly. Such a cosmic event will result in the formation of a single elliptical galaxy. This type of collision isn't unique, as the universe has a long history of such events. However, our direct participation is what makes it an event of interest to us. In addition, the predicted collision of the supermassive black holes at the nucleus of the two galaxies adds more mystery to this celestial show, suggesting a complex and deep nature of cosmic evolution. The merger is predicted to produce explosions from matter being engulfed by the black hole, which will release extensive radiation. This process offers important data about how galaxies move throughout their lifespan and how black holes affect this evolution. However, it raises a crucial question: what will happen to our solar system after this merger is formed? Far from a total destruction of the solar system's orientation and conditions could be altered significantly. This implies possible orbit shifts or even ejection from the newly emerged galaxy. To understand this mechanism, scientists can study the magnitude of similar events happening and contextualize the eventual fate of our own galaxy. It is crucial to understand that a collision between stars is a rare event in space because of the vast intergalactic distance. However, the gravitational change could disturb stars' stable orbits, causing some stars, including our Sun, to change trajectory. Such a change could drastically disrupt the climate on Earth. One of the most critical changes humans can experience is moving further away or closer to the Sun. This could lead to either warming or cooling effects. A warmer climate could make ice caps melt and sea levels rise, while a colder one would lead to a new form of ice age. On top of that, the geometry of such a setup might interfere with radiation levels coming to the Earth, creating even more challenging conditions. In essence, the merger of the Andromeda and Milky Way systems illustrates the complex relationship between celestial bodies. As the black holes in both galaxies get closer over time, their gravitational actions may increase the flow of high-energy particles that can reach Earth, ultimately causing enhanced cosmic radiation to penetrate our atmosphere. The potential surge in radiation levels could be a threat to ecosystems on our planet, as it may increase mutation rates in populations and affect biodiversity. The redistribution of Earth's natural orbit or its axis, which would follow from the black hole merger, can be expected to interfere with the way habitats are spread. How organisms will survive in climate zones that may become unfavorable is one of the effects of climate change experienced globally through shifts in biodiversity and ecosystem structures. Although a few species may flourish under the new circumstances, some would die off, and others would be highly endangered. The merger will likely lead to the creation of new stars as clouds of gas from the nebula come together and get compressed. If this process occurs close to our solar system, radiation from these juvenile stars could alter the environment, resulting in a drastic change in the climate and the entire ecosystem. While it is true that these events define the grand narrative of cosmic evolution, it is important to put them in context and understand the timeline. The resulting events of the collision are far away, billions of years into the future, where humanity may have changed significantly. We may already be living in different parts of the galaxy or beyond it. The knowledge obtained from exploring the Andromeda Galaxy appears to be the key to understanding the evolution of our own galaxy and its future. The perceived differences between Andromeda and our galaxy can be used to develop more precise models for galactic dynamics and evolution. The reassessment of Andromeda's size and mass is a solid endeavor because it directly informs our understanding of the Milky Way and its structure. As a result, it has shattered our initial assumptions about Andromeda and the need to reconsider its significance in our galactic neighborhood. Recent data suggests that both the Milky Way and Andromeda galaxies are comparable in size rather than ours being much bigger. This contradicts our understanding of the Milky Way's role within the local group of galaxies and the amount of gravitational force such a galaxy exerts. While the Milky Way today appears as a barred spiral galaxy, its structure could change due to its interaction with the Andromeda Galaxy, an interaction that will most certainly happen in the near future. As such, observing Andromeda's evolution helps in profiling the mechanisms behind the major galaxy transformations. By examining Andromeda's present status and estimating the trajectory of the subsequent collision on the Milky Way, much can be inferred. Cosmologists would model the possible changes in star formation rate and the distribution of gas and dust, in addition to the changes in both galaxies' cores. Creating the model is possible thanks to the technological advancements in astronomy that have dramatically changed the scope of space studies. This has made each expedition greater than the previous one. The journey began with the invention of the telescope in the early 17th century, which led astronomers to see the orbits of moons around Jupiter and the phases of Venus. Little by little, telescopes became more sophisticated. The late 19th and early 20th centuries witnessed the design of more massive and mightier telescopes. The world beyond the Earth became more accessible while astronomers uncovered new celestial bodies like Neptune. Though the ground-based telescopes faced obstacles such as atmosphere and light pollution, they managed to provide remarkable insights into the mysteries of the universe. With the introduction of the Hubble Space Telescope in 1990, we made a remarkable step forward in space exploration. Not only did Hubble allow us to view the universe from a point further above Earth's atmosphere, but it also nearly eliminated Earth's disturbance smearing view. This resulted in more clarity, depth, and observations than ever before. The Hubble aided a better understanding of black holes, the universe's age, and the current expansion of space. The Hubble Space Telescope was accompanied by the Chandra X-ray Observatory, the Spitzer Space Telescope, and some other space telescopes, which further contributed to our knowledge about the universe. They observed the cosmos from space, bypassing the obstructions encountered on Earth. Apart from light telescopes, radio, infrared, and X-ray observatories have also greatly expanded the astronomers' options of sky observation. With these devices, astronomers are not only able to detect but also study many kinds of phenomena. This includes the universe's microwave background radiation, star formation regions, and the remnants of supernova explosions. However, dark matter is still one of the most mysterious yet intriguing factors that scientists are struggling to understand. It occupies roughly 90% of a galaxy's mass while being undetectable. Typical of dark matter is the fact that it cannot be detected using standard detection means. Unlike other astronomical objects that are seen, dark matter is detected only through its gravitational effects on visible objects, radiation, and the large-scale structure of the universe. In the Andromeda observational data, dark matter originates from the galaxy's rotational dynamics. Stars in its edges display rotational speeds comparable to those at the center, which is contrary to the predictions of earlier theories. This implies that several unseen elements attributed to dark matter are surrounding and influencing the galaxy. In addition to the Andromeda observations, it became clear that there is a massive amount of dark matter in the halo that extends far beyond the visible stars. By means of the gravitational field, Andromeda's halo has a significant influence on the motions of satellites, galaxies, and star clusters that rotate around Andromeda. Through the investigation of orbital movement, astronomers were able to identify how the amount of dark matter is distributed in a galaxy. Such studies inform us that the dark matter halo of Andromeda isn't only massive but equally outstretched, encompassing a million light-year radius from its core. Additionally, the structure of dark matter in Andromeda is not regular. The mass is concentrated close to the galactic core while getting more dispersed outwards. This distribution alters the formation and evolution of stars with the gas clouds throughout the galaxy, creating more spiral arms and adjusting the rate and location of new star formation. Besides that, dark matter is hypothesized to have acted as the main force during the merging and collisions of galaxies, shaping the final forms of these cosmic events. Therefore, discovering the secrets of dark matter is an essential quest in modern astrophysics. It is expected to pave the way for profound understandings regarding the essence and the evolution of the universe. The impending collision between Andromeda and the Milky Way is not merely a cosmic merger of two galaxies but also an interaction of their vast dark matter halos. These unseen halos enveloping both galaxies will be transferred into the movement of the collision and will be essential in how the post-merged galaxy will look. The observations of Andromeda helped scientists fill the gaps in understanding the formation and evolution of galaxies when the universe was in its infancy. Through careful deep analysis of their structure, astronomers essentially reveal the small processes that give birth to galaxies and change them over billions of years. These processes comprise the birth of the spiral arms and the growth of a central bulge, which typically occur after pairs of galaxies glide and fuse. This understanding helps cosmologists to adjust galactic models that are appropriate for the universe. Signals from Andromeda also contribute to improving the accuracy of the cosmic distance ladder. Through the comparison of the relative spatial distributions of the nearby stars and the broader universe, the accuracy of techniques estimating the size of the universe can be further improved. This calibration is critical as it explains fundamental cosmological parameters such as the Hubble constant, which is used to read the expansion rate of the universe. Moreover, by looking at the stars that make up the Andromeda Galaxy and checking their chemical composition, one may learn about the processes of star birth and death and the chemical enrichment of the universe. These revelations allow us to truly understand how nucleosynthesis and similar chemical enrichment processes happened in the early days of the universe.